In this video, I will give you a refreshment of propositional logic and its decision problem SAT. Propositional logic is very old. Its roots date back to the ancient Greeks, and since then it has been very well investigated. Today it finds applications in various fields like in philosophy, in maths, or in computer science, and we will use it for solving various reasoning tasks. The language of propositional logic is very simple. We have the atomic propositions and we combine them by using Boolean connectives like conjunction, disjunction, negation to more complex formulas, and these we can again then combine by these Boolean operators. We do not have any arguments to the propositions as in first order logic. We have no functions, no terms, no quantifiers. Yeah, we really have only atomic propositions and Boolean connectives and parentheses. And if we have now given a Boolean or a propositional formula, we want to know if this formula is satisfiable. So what we are asking is the following: is there an assignment to the propositional variables or the atomic variables that occur in the formula such that the formula evaluates to true under this assignment? And this is the decision problem of propositional logic, which is also well known as SAT. SAT is the archetypical problem of the complexity class NP, the non-deterministic polynomial time decision problems, which have the following characteristics. Searching for a solution is most likely very hard, so it has not been proven, but it's well assumed that this is the case. And checking a solution candidate is very easy. What does this mean in the case of SAT? If we have a propositional formula which contains n variables, then it's not so hard to see that such a formula has 2 to the power of n potential solutions. Yeah? Because each variable can be either true or false, and so if we have n variable, this gives us 2 to the power of n combinations, meaning that the search space is exponential in the number of variables a formula has. Okay, this is very huge, but checking a solution candidate is cheap because we simply can plug in or assign the value of the variable and use the meaning of the connectives in order to decide if the formula is true or false. This can be done very easily, and this is in contrast to searching for a solution. And compared to decision problems of other logics, it's still very easy. It can be harder, although we have this enormous search space. And there are a lot of problems which fall into the complexity class MP, and therefore it's very convenient to solve them, to use very advanced SAT solving technology, translate these problems to SAT, use a SAT solver to solve them, and take the solution of the SAT solver and interpret it for the original problem. Yeah, and now let's define how a propositional formula looks like. So first of all, we have the atomic propositions. These are statements that are either true or false and which cannot be further disassembled. So for example, Alice comes to a party, such a statement: one has to wear a shirt, or it rains. And then with connectives we can combine propositions to more complex propositions, and from them we can build even more complex propositions and so on. So for example, Alice comes to a party, Bob comes to a party, but not Cecile. Here we have 3 atomic propositions which we combine. One has to wear either a shirt or a tie, so here we have an exclusive or if it rains, then the street is wet, which can be written down by implication. More formally, let us introduce the syntax of a propositional formula. We build a formula always over some propositional variables, and here we define the language of propositional logic over the set of propositional variables which are contained in P. So these are our atoms, and now we define what is the set of all well-formed propositional formulas, and this is the smallest set, so it does not contain anything else except what is defined here, such that we have the truth constant in this set, we have the variables from P in this set. If we have a formula or an element phi in the set, then not phi is in the set, and if we have two formulas phi psi in the set, then they can be combined to a new formula which is in the language of propositional logic by using disjunction, conjunction, equivalence, or implication symbols. Yeah? And we call L, the set, the language of propositional logic, and these elements are propositional formulas. Here I have several examples. We have top, we have the variable a, we have not a, and here we have some more complex formulas. Yeah? So this is how propositional formulas in principle could look like. Now we give the whole thing a meaning. So what is the semantics of propositional logic? We define the semantics with respect to an assignment of the variables, meaning that we have a function which maps each variable of P to a Boolean value, which is true or false, and then we can define an interpretation functions which gives a meaning to every element of L based on the assignment that is given, and a propositional formula is either true or false. And now we have the following rules how the interpretation function is defined. So if the formula is just truth constant top, then it always evaluates to true. We write true by 1. If the truth constant is bottom, then it always evaluates to false, which is written by a 0. If we have a variable, then it's interpreted by the value given by the assignment. If we have a formula not phi, then this formula is true if and only if phi is false. If we have a disjunction phi or psi, then this disjunction is true if and only if either phi evaluates to true under the assignment or psi evaluates to true, or both evaluate to true. Yeah, and negation together with disjunction is functionally complete. Functional completeness means that we can express any other operator by the mean of these two operators. Yeah, so if we want to have, for example, an a conjunction, so if we want to have A and B, and we have only disjunction and negation at hand, then we can write this down as not A or not B. Yeah? And you can check with a solver or a truth table that this is indeed the case. Yeah? So in principle we could define the meanings of the other operators as well, but we can also express them only in terms of negation and disjunction. We call an assignment a satisfying assignment if the formula evaluates to true under this assignment, so if and only if the formula evaluates to true under this assignment, and we call an assignment a falsifying assignment if the formula evaluates to false under this assignment. Yeah, reads in both directions. And a satisfying assignment is called a model, and a falsifying assignment is called a counter model. I have a quick example. Let's consider the formula A or B and not A or not B. Then if we do a truth table, we have 4 possibilities because we have 2 variables. So now let's quickly see what the value is of this formula. So if both of A and B are assigned false, then the formula evaluates to false. Here in second and third assignment it evaluates to true. Third assignment it evaluates to false again. Here we have 2 models. And in the first and in the last row, so the assignment which assigns same values both to A and B are counter models. Okay. Yeah, now we can express the satisfiability checking also as a simple algorithm. Maybe for some of you this is much easier to read. So we have an algorithm that takes a formula phi and returns 1 if it is satisfiable, so it returns true, and otherwise it returns false if the formula is not satisfiable. And we proceed, this algorithm proceeds as follows. If phi contains a variable x, so we pick some variable from the formula first, and then we pick some truth constants, bottom or top, one of them. And what the algorithm does, it replaces x by the truth constant that was picked. Yeah, and then it evaluates the modified formula recursively. So this is the formula where x is replaced by the truth constant. And if this evaluates to true, yeah, so if the function here returns true, then it returns true. If this is not the case, so in the case the formula is evaluated to false, then this means the value that was picked or the replacement was not leading to a satisfying assignment, and therefore the constant is negated. So top becomes bottom, bottom becomes top. This is what we mean here with this notation with the overline. And again we evaluate the formula which is modified in the sense that the variable is replaced by this truth constant or by this negated truth constant, and then we return, or it returns the value that is found during this evaluation. Yeah, and if the formula does not contain any variables anymore, then what does it do then? If the formula is simply top, it returns true. If it's bottom, then it returns false. If the formula is a formula not psi, then it evaluates psi and negates the returned value. Yeah, so if psi is true, then not psi is false. Then if psi is true, then evaluate psi returns true, and the negation gives us false. And the other case is similar. Then if we have a formula, so if this formula phi is a formula phi prime and psi prime and psi double prime, then we evaluate psi prime, we evaluate psi double prime, and conjunctively combine the returned value. So if both are true, then true is returned. If at least one of them is false, then false is returned. And the same we do for the disjunction. So if the input formula is a disjunction, then we evaluate these two subformulas separately and combine the returned value by disjunction symbol. Yeah, here is some important terminology which we will use often during this lecture, and which also transfers in a similar way to other logic. A formula is satisfiable if and only if there exists an interpretation such that the formula evaluates to true under this interpretation. So in principle we need also an assignment that makes the formula true. We call a formula valid if every interpretation and if the formula evaluates to true under every interpretation. So if every assignment is a model, a valid formula is called a tautology. A refutable formula is a formula which has a counter model, and a formula is unsatisfiable if there is no model. And an unsatisfiable formula is also called a contradiction. A satisfiable formula is possibly valid, but it can also have a counter model, so it's not necessarily valid. It's possibly refutable, and it's obviously not unsatisfiable. A valid formula is definitely satisfiable, it's not refutable, and it's not unsatisfiable. A refutable formula is possibly satisfiable, possibly unsatisfiable, but not valid. Yeah. So if a formula is refutable, then it could have still a model. It could also have no model, then it's unsatisfiable, but it's definitely not valid because it has a counter model. And an unsatisfiable formula is refutable, not valid, and not satisfiable. Here I have an example. This formula contains 3 variables a, b, and c, and we are asking if this formula is satisfiable. We decide this by using a truth table, and first assignment is setting all variables to false. When we look at the formula, then we have some parts of the formula which evaluate to true. So for example, not A is true, but these parts are marked in green, and then we have some parts which are false. These are colored red, and this formula has a very special structure. As we will see, we have conjunctions of disjunctions, and a conjunction is true if and only if both subformulas or all subformulas are true, and here we have a subformula which is false because it contains only red symbols, so the formula omega evaluates to false under this assignment. Now we can try another assignment, and again we find a constraint. Here in this case it's A or B or not C, which evaluates to false under this assignment, and this we continue, and there are many assignments which are counter models, and just at the end, when we consider the assignment which sets all variables to true, we found an assignment that's indeed a model. This means that every, I now call it clause, disjunctions are clauses, every clause contains at least one variable that is not negated. Yeah, here we have the C, here we have the B, we have the B and C here, we have an A here, here we have an A, we have AB here, and we have BC here. Okay, so this formula is satisfiable. Yeah, then some important equivalences which you should know. I go very quickly over this, but this you should really know by heart. These are core properties of propositional logic. So conjunction is commutative. You can swap the order of the subformulas and it doesn't change the value of it. So if you have phi and psi, then this is the same as psi and phi, same for the disjunction. Then we have associativity, phi and psi and gamma is the same as psi and phi, and gamma. So we may change the order. We may change the position of the parentheses. Doesn't matter how we put parentheses. Same is for the disjunction. Then we have absorption. If we have phi and phi or psi, then this is the same as phi. Dual version for the disjunction. If we have here next phi and psi or gamma, then this is the same as phi and psi or phi and psi and gamma. So this is distributivity. Then a very important property are given by the laws of De Morgan. If we have not phi and psi, then we can shift the negation inside and get not phi or not psi. Same for not phi or psi. The connective simply flips. Then what is also important is that we can rewrite an equivalency in terms of an implication. So if we have phi and psi are equivalent, then this is the same as phi implies psi and psi implies phi. Here is also an other notation for this. Then if we have phi or psi, then this we can replace by not phi implies psi. And if we have phi implies psi, this is the same as not psi. Not psi implies not phi. So here the order or the position of the two formulas is switched and they have to be negated. If we have phi and not phi, this is the same as bottom. If we have phi or not phi, this is the same as top. So this is the rule of complement. Here we have a contradiction, here we have a tautology. Then if we have double negation, then this is the same as the plane formula. If we have phi and top, this is the same as phi. If we have phi or bottom, this is the same as phi. If we have phi or top, then this is the same as top. And if we have phi and bottom, this is the same as bottom. Not top is the same as bottom, and not bottom is the same as top. So these rules you should know. And there's not much to say it. Then I would like to recall a certain terminology. A literal is a variable or a negated variable. Could also be a negated truth constant. Here we have some example: x not x, y not y, bottom not bottom, top not top are also literals. Then a clause is a disjunction of literals. So we have literals which are as defined before, and we combine them by logical OR. There are some clauses with a special name. A unary clause is a clause of size 1. The size of a clause is given by the number of its literals. The empty clause is a clause of size 0. It's also written with this bottom symbol of the truth constant force. And here are some more examples. We have this binary clause x or y. We have a ternary clause not x or x prime or not x double prime. And here we have two unit clauses x and not y. Dually we can define a cube. This is simply a conjunction of literals. Then some specific or some special formula structures. We have negation normal form and an F, which is defined as follows. So literals and truth constants are in negation normal form. Phi and psi is in negation normal form if and only if phi and psi are in negation normal form. So if we have formulas in negation normal form, we can combine it with a conjunction. Same with a disjunction. So if we have two formulas in conjunctive in negation normal form, we can define it. We can combine them either by disjunction or conjunctions. No other formulas are in negation normal form. So here we do not allow formulas that contain equivalence or implication, and we allow negation only to be in front of a variable or a truth constant. Yeah? We do not allow formulas where we have something like this. So for example, not A or B is a propositional formula, but this formula is not in negation normal form. Okay. Yeah, so to summarize, the formula in N and F contains only conjunction, disjunction, negations, and negations occur only in front of variables or truth constants. A propositional formula is now in conjunctive normal form. If it is a conjunction of clauses, this is a much more restriction for the syntax. Yeah? So we have only conjunctions of clauses. And obviously a formula in conjunctive normal form is in negation normal form, and a formula in conjunction normal form is equivalent to the to top. So if there is no clause, then this formula is always true, and this means that so if it contains no clauses, it's always true. Yeah, clauses are constraints, and the more clauses I have, the more likely, under quotes, the formula is false. And if I have a formula in C and F, it's very easy to check whether this formula can be refuted, so if it can be set to false. If we go here to our example, this is a formula in C and F. We have two clauses, A or B, and the second clause is not A or not B. And in order to check if it's refutable, we simply take a clause and see if we can find an assignment that makes it false, and this works by making all literals false. And here, for example, we have literals A and literals A and B, and if we set both to false, then this clause is false, and then the whole formula is false. Yeah, and what is difficult, or what is computationally expensive, is to find an assignment that satisfies all clauses, and it can be shown that decision problem of formulas in C and F is NP complete, and in fact it is sufficient to have clauses of size at most 3 in order to have an NP complete decision problem. And any problem, any propositional formula can be translated to an equivalent problem in conjunctive normal form, and this conjunctive normal form has a lot of advantages. So we have in principle sets of set as a data structure, and there are a lot of techniques that work on this restricted structure either better, or they do not work on arbitrary formulas, simplification techniques. And for this reason, CNF is the input language of most such solvers. So CNF solvers can solve, CNF solvers have the full power of propositional logic, or they can decide SAT, but they process only formulas in this restricted format, and the specific format is called Dimex format, and I will introduce this format in another video. Okay, and if I have given an arbitrary formula, the question is now how to transform a formula to CNF. This I would also like to quickly show you. So in the first step I transform it to n and f, and yeah, here the problems already start. I could simply do it by using these rules we have seen before, and multiply things out. So for example, if I have phi is equivalent to psi, then in the first step I could replace it to not phi implies psi and phi no, and psi implies phi, and then proceed with not phi or psi and not phi or psi, not psi or phi, and then I could proceed with this, and hopefully at some point I have only clauses left. Problem is, if now let's think about the situation where we have say A and B, or C and D. Yeah. Now I could multiply this out, and then I would get A or C and D. And B or C and D. Oh, and what I have here is now I have a copy of C and D. So first it occurred only once, and now suddenly it occurs twice. And yeah, it could be that this formula is deeper nested, and then I would copy these huge subformulas very often, and then I suddenly have a blow up of the formula size. Yeah, and if I do it like this, this could in fact lead to an exponential blow up. And so what I have to do is I have to do the normal transformation in a more clever way when I have nested subformulas, and this works with the so-called Zetin transformation. So for a complex subformula, we generate a fresh variable, a variable which does not occur in the formula. We replace the subformula by this variable, and then we add a definition saying this subformula is equivalent to the newly introduced variable, and transforming this equivalence to a normal form is cheap, because here we do not have a complex formula, and we can simply, it's cheap to translate this to a CNF formula. And then we collect all the constraints in a big disjunction. Let's have a look at some example. Do I have a good formula to start with here? No. Let's before erase the page that we have more space. Okay. Now let's consider. Yeah, let's consider the formula A and B, or C and D. Okay, this is a formula very similar as before. And what we do in the first step is we introduce a fresh variable for A and B and get, so let's call the variable X we introduce here. Let's call the variable Y, which introduced for the second part. And then if we replace A and B by x, we get x or y for replacing this c and d by y. And now in the next step we have to introduce the definitions. And now the definition says x is equivalent to a and b. And if I do it slowly, then this is the same as x implies a and b. And a and b implies x. And what is this? Then we have not x or a, and not x or b, and we have a third clause, not a or not b or x. Yeah, so we get 3 clauses, and it's not further necessary to expand it. Yeah, and the same I do for here for the C and D, and then we get not x or a, and not x or b, and not a or not b or x, and we get not y or c, and not y or d, and not not c or not d or y. Yeah, this would be this simple formula be transformed by introducing new variables for these cubes here. And if I have a more nested formula, so this is very simple, and here we do not really see the advantage, but if we have a more nested formula like a or b and c or d and e, then what I would do is first introduce a new variable for this. Let's call it x1, then a new variable x2 for this. So I would say x1 is equivalent to d and e, x2 is equivalent to c and x1. Then I introduce a variable x3 and say x3 is equivalent to b, and here I need an or, and is equivalent to b and x2. And finally I introduce a variable x4, and I say x4 is equivalent to a or x3. Yeah, and here you see I never have complex formulas here, but I have either definitions or in this case it could be literals. Yeah, and so the transformation does not lead to a considerable blow up. So we do not have an exponential blow up here in the formula size. The trade-off is that we introduce new variables, and therefore the Sat solver does not so the formula what we have is satisfiability equivalent, meaning the new formula is satisfiable if and only if the original formula is satisfiable, but it's not equivalent because the new formula has different models. But for deciding satisfiability, this property is enough. Okay. Yeah. Because of the new variables, the formulas are not logically equivalent. And on the following slides, I've written down how to perform the normal transformation of the definitions. Yeah. So, for example, if the label replaces a negative literal, then we have x is equivalent to, for example, not y. Then we first replace the equivalence by two implications. Then we replace the implications by disjunction and negation. And that's it. Then we already have C and F. Here I have written down how to perform the normal form transformation for a disjunction. Here we have the label, here the disjunction, here we have the label, here we have the label, and here we have the disjunction. Again, we first replace the equivalence and then the implication, and we are there. Yeah. Similar, it works for the conjunction. For the equivalence symbol, there's a little bit more to do in order to replace the inner equivalence symbol and so on. Yeah, and I would like to conclude this video with some discussion how to solve formulas in conjunctive normal form and how the basic concepts of a solver work. And for this purpose, I introduce a very simple but extremely powerful technique, which is called binary constraint propagation. And before we look at the definition, let's consider an example. Yeah? Assume I have a formula A or B and not A or not B, and A or C or D or E, and what else? Maybe A or C, and I put the n symbols explicitly here, and here it is A and negate, and then I have a unit clause A. Okay, and here this unit clause has an interesting property. Yeah? If I have a unit clause, then I have no choice how to assign the variable of the literal that is in there. Yeah? Because if in this case I would set A to false, then the unit clause would be false and the whole formula is false. Yeah? Here the only choice I can make is to set A to true. Yeah? So I'm forced to do so because otherwise the formula would evaluate to false. And if I set A to true, then I can propagate this assignment, and all clauses containing the literal A can be removed because they become true. They cannot falsify the formula. And all the clauses that contain not A are shrinked by removing this not A because it's set to false. Yeah? So A is set to true, so not A is false. And what I get then is a new formula, and I get the formula not B and not C. Yeah? And this formula is satisfiable equivalent, meaning that if this formula is true, if the formula on the top is true, then also the formula below here is true. And if the formula below here is true, is satisfiable, then also the formula above here is satisfiable. Yeah. So we do not talk about assignments and that they have to be satisfiable assignments for both formulas, but here we only require that the two formulas have the same true value, so that the simplification technique does not change the value of the formula. Okay, and now we can proceed. Now we have again two unit clauses, and we can set B to false. Then we simply remove this clause, and this is equivalent to satisfiability equivalent to not C. And for this we can find, now I did the wrong symbol, and for this we can derive that this is satisfiability equivalent to top, because we have here then one literal, now I mark it in red, in a unit clause. We set literal to true because otherwise the formula would be false, and then we can derive that the formula is true. Yeah? So by simply applying this unit propagation, we could design the true value of the formula. So this is not so difficult. And now let's look at an example where we have the following situation. Say we have A or B, and we have not A or not B, and say we have not A in the unit clause. Okay, then this is obviously satisfiability equivalent to the formula which I obtain by removing the positive occurrences of A and then removing the clause with the unit, and what I get is a formula B and not B. Okay, and this is obviously satisfiable equivalent to bottom. Yeah? So here we have the case that we obtain the empty CNF, that we derive the empty clause which is false. Yeah? Because say we choose this unit clause to decide the value of B. Here we have to set B to true, and if we propagate it, then here we have not B, and if B is true, then this not B is false, and therefore we remove the not B, and we obtain one clause which does not contain any literal, and such a clause can never be true. Okay, so we can now write this down in a more formal way. If we've given a formula phi and C and F, which contains a unit clause C with one literal L, then PCP of phi and L is obtained from phi by removing all clauses with L and removing all occurrences of not L. Yeah, so we remove all clauses that contain the literal, and we remove all negations of this literal. PCP can trigger other applications of PCP, as we have seen in the example before. Then if we get the empty clause, then we know the formula is unsatisfiable. If we get the empty CNF, then we know the formula is satisfiable, as there are no constraints are left which could be falsified. Having PCP, we can now formulate the following solving algorithm for formulas in CNF. So we first of all have an infinite loop, and we do not implement a recursive algorithm, but a non-recursive solving algorithm. And when we enter the loop, we first perform PCP until fixed point, so we apply PCP until there is no unit clause left. If the formula is the empty formula after this PCP applications, then we return true. Otherwise we proceed, and there are now two cases. There is the case where the empty clause is in the formula, and there is the case where the empty formula is not in, the empty clause is not in the formula. Let's start with the second case. If the formula has a literal that occurs in the formula, we select such a literal, any, and we have a stack where we store assignments which we still have to try. We store not only that we have to try the complement assignment of L, which is this L bar, but we also store the current state of the formula. And what we do now is we add L as a unit clause to the formula. And obviously this forces the variable of L to be assigned a certain value. And this happens here again in BCP. Okay, and then again we check if the formula is empty. After BCP, then we return 1. Otherwise, we proceed selecting a literal if the formula does not contain the empty clause. If the formula contains the empty clause, then we check if the stack is empty. If the stack is empty, then this means that there is no literal which we have to consider with its opposite value. And if this is the case, then we return false. Otherwise, we take the topmost element from the stack, so we get literal and the status before the complement of the literal was assigned, and we add L as a unit clause to the formula and proceed in this loop. Yeah? And this gives us the basis for a very powerful decision procedure in practice for highly efficient QBF solver, not QBF, for highly efficient SAT solvers. This is not enough. Many more techniques are needed which optimize the search in this huge search space. There are learning and non-chronological backtracking techniques so that we can ignore certain assignments of variables. There are reset strategies when we want to look in a different part of the search space. Phase saving, then there are special data structures, very clever heuristics for selecting variables, and very crucial to solving is also pre-processing and in-processing, which apply techniques before or during solving in order to simplify the formula, which is still having the same truth value, but which might be easier to solve. And this kind of algorithm is implemented in many state-of-the-art solvers like Klingeling, KISSAT, but also in solvers like Minisat, Picosat, and Klingeling. Yeah? Many of them are solvers that come from Linz. And this DPLL approach is not only used in SAT, but also in other logics like QBF and SMT. And current hot topic is parallelization of this approach. At the moment, it's not clear how to do it, but there is progress. Okay, so to summarize, SAT has written a very successful story. It's used for practical problems of millions of variables, and for solving SAT, there are very good tools available, and this is the reason why many different research communities and industry use SAT solvers to solve their problems. SAT problems can be found in many application areas. In this course, we will consider planning problems formulated in SAT. For SAT solving, there's a huge research community behind it, with a conference which is called SAT, where people speak a week only about SAT solving. Then there is the annual competition where SAT solvers are compared, so solver developers can submit the solvers there, and independent researchers perform an evaluation. This is important to ensure progress of solving technology, because there are a lot of challenges like correctness of the code, efficiency, and so on. And this is evaluated in these competitions, and it's fun for competitors and also for the people who watch it. Standard input format of most solvers is CNF, conjunctive normal form, and there's also a rich infrastructure for related tasks. For example, if a formula is unsatisfiable, we want to know if the result is indeed correct, and we cannot check every possible assignment if it's indeed not a model, but what we have to do is we have, or what is done in practice is the solver dumps a proof, and this proof is checkable by external tools such that it can be assumed that the tools which are used for checking are correct. They are much simpler than a solver, and then even if the solver is buggy, we know if the very specific result is correct or not, because we have a certificate in terms of a proof which is checked by a solver, by a checking tool.